Let me guess. You tried AI, it hallucinated something completely wrong, and now you're back to doing everything manually while complaining that AI does not work. Maybe you're a developer who asked it about your codebase, and it confidently explained functions that don't exist. Or suggested using deprecated APIs your team abandoned 2 years ago. Perhaps it recommended architectural patterns that directly contradict your team's decisions. Or you're in ops, and it gets even worse. You asked about your backup policies, and it invented procedures you've never implemented. You requested help with the Kubernetes deployment, and it suggested configurations that violate every security standard you have. You wanted it to troubleshoot a production issue, and it gave you generic advice that would take down your entire cluster.
The AI is completely delusional. It's making up functions that don't exist. It has no idea what we're building here.
So, now you're one of those people. You've probably written a snarky post about it. Maybe even a blog titled, "Why AI Isn't Ready for Real Engineering Work." Here's the uncomfortable truth. You're doing it wrong. That's it. You're asking AI about your team's coding standards without giving it access to those standards. You're expecting it to know why you chose PostgreSQL over MongoDB without feeding it your architectural decisions. You're demanding it follow your deployment procedures while keeping those procedures locked away in various tools and documents.
Your computer cannot see into your soul. What did you expect? Mind reading.
But sure, keep blaming the technology. Keep writing boilerplate code manually. Keep copy-pasting from runbooks. Keep believing that AI is the problem. Or maybe stick around and learn why your AI experiments failed and, more importantly, how to fix them. We'll take a quick break for me to introduce you to Outskill, the sponsor of this video. Here it goes. A significant percentage of companies are already using AI, and many are laying off people because of it. People fear AI will take their jobs this year. Now, that probably sounds scary, but here's what's not obvious. They're also hiring. They're hiring people who understand AI, who can use it, who can build it. And this isn't just about jobs. If you run a business, freelance, or are building something of your own, AI is not optional anymore. It's leverage. The ones who learn AI will now outrun those who don't. So if you want to stay ahead, hire better, build faster, start learning AI today. And that's where Outskill comes in. They have a 2-day AI mastermind happening this weekend on Saturday and Sunday. 2 days with expert mentors. 16 hours of learning, 10 plus AI tools. You go from an AI rookie to an AI pro and stay relevant. Now, here's the important part. This training normally costs $895, but Outskill is giving away 1,000, and I repeat, 1,000 free seats to my viewers of this channel for the next 72 hours. The link is in the description over there. Check it out. Alternatively, join the WhatsApp group for more information. And now let's go back to the main subject. Large language models possess vast knowledge from their training on internet data, but they know nothing about your organization. They understand PostgreSQL syntax, but not that your company mandates using Cloud Native PG for all database deployments. They can write perfect Kubernetes manifests, but they don't know your team requires specific labels, annotations, and resource limits. They grasp software engineering principles, but are unaware of your architectural decisions, your security policies, or operational runbooks. That knowledge gap becomes critical when deploying AI agents in production. Consider a developer asking an AI agent to deploy a new database for the user service. The model can generate a generic PostgreSQL deployment, but without your organization's context, it won't know to use Cloud Native PG. It will not know how to apply your required security policies. It won't follow your naming conventions, and it won't configure the backups according to your disaster recovery standards. The challenge intensifies when we examine how AI agents interact with existing systems. Take Kubernetes APIs. While amazing, excellent, for operations, they weren't designed for the exploratory semantics queries that AI agents need. When a developer asks, "Show me all your databases," the AI agent faces an immediate problem. The developer might say databases, another might say or ask for DBs, a third could request PostgreSQL instances, and someone else might query data sources. To Kubernetes, those are completely different things. It only understands exact resource types, deployments, stateful sets, PostgreSQL something, or RDS instance, and so on and so forth. But wait, you might say or ask, can't AI just query all possible database releases resource types? That's exactly what it must do. The agent has to know every possible resource type that could be a database. Stateful sets, running PostgreSQL, cloud-native PG clusters, cross-plane RDS instances, Helm-deployed MongoDB, and so on and so forth. Each requires separate API calls, returns different schemas, and uses different terminology. There's no unified way to ask, hey, show me all database-related resources, because Kubernetes does not understand that those are all conceptually databases. It sees them as completely unrelated resource types. The root of this problem is that APIs are not designed for humans. They're designed for machines. That's why we need tools like Terraform to translate between human intent and API operations. APIs excel at precise, unambiguous operations. Create this exact resource, delete that specific pod, update these particular fields, and so on and so forth. We interact with AI using natural language, the same way we interact with other humans. When someone asks, hey, show me our databases, they're expressing human intent, not the API call. While AI agents can use machine-oriented APIs for operations, they struggle a lot with discovery because APIs weren't designed to understand that database, DB, PostgreSQL, and data storage might all refer to the same concept. Security and governance policies present an even greater challenge. Your kernel policies prevent misconfigurations effectively. No doubt, but they're right only from an AI's perspective. When asked, hey, can I expose this database to the internet, the agent must retrieve every policy file, parse all rules, understand their conditions, and determine which apply. But isn't this the same question we answered 5 minutes ago? You might wonder when another developer asks, is public access allowed for PostgreSQL? Then third asks, can we add an internet-facing endpoint to our database? And the fourth simply types external DB access. Those are all the same questions expressed differently, but without semantic understanding, the AI treats each as a brand new query. It must scan all policies again because it cannot recognize that exposed to internet, public access, and external endpoint all mean the same thing. This expensive discovery process repeats endlessly because there is no efficient way to index and retrieve policy knowledge based on meaning rather than exact text matches. Beyond infrastructure, consider the wealth of knowledge trapped in your organization's documents, issue trackers, runbooks, and wikis. How do I fix slow database queries in production? An engineer might ask. The answer exists in your organization, but where? The root cause analysis might be in ticket JIRA 1234 titled Investigation of CPU Spikes. The solution could be documented in a runbook called PostgreSQL Tuning Guide. Additional context might live in a Slack thread about connection pooling issues, and a wiki page on, database best practices. But here's the challenge. None of those documents mention slow queries explicitly. They talk about performance degradation, high latency, connection timeouts, or resource optimization. An AI agent trying to help cannot efficiently find all relevant information because those systems organize information by location, like which folder, which channel, which project, rather than by meaning. It doesn't understand that slow queries, performance issues, and high latency are all related to the same problem domain. Now, a clever one, might think the solution is to train custom models on your organization's data. However, this approach quickly proves impractical. Your documentation changes daily, new policies are added weekly, and systems evolve constantly. Training custom models is expensive. It's time-consuming, and by the time a model is trained, its knowledge is already outdated. You'd need a continuous model training pipeline, transforming AI assistance from a production tool into a complex MLOps challenge. Coding agents, on the other hand, like Cloud Code and Cursor, can technically access all those systems through their tools. They can query Kubernetes APIs, read documentation, search through tickets, and parse policies. Once they understand what needs to be done, they excel at executing operations through those same APIs. But the discovery process remains painfully inefficient. Finding the right information based on semantic meaning rather than exact matches is the place where they really struggle. What we need instead is a way to dynamically provide the AI with the right organizational knowledge at the right time based on the context of each request. But how can we efficiently store, index, and retrieve this diverse knowledge in a way that the AI can understand semantically rather than just matching keywords? How can we ensure that when an agent needs to know about database deployment policies, it can quickly find all relevant information regardless of where it's stored or how it's phrased? This is the challenge modern AI agents face, and solving it requires rethinking how we store and retrieve organizational knowledge. Vector databases are specialized storage systems designed to handle semantic relationships rather than exact matches. Unlike traditional databases that store data in rows and columns or documents, vector databases store information as mathematical representations called embeddings. Think of it this way. In a traditional database, database DB and data store are three completely different strings. In a vector database, they're stored as points in space that are close together because they share similar meaning. When you search for PostgreSQL performance, it can find documents about database optimization and query latency because it understands these concepts are related, even though they don't share the exact same words. This semantic understanding makes vector databases superior to traditional databases for AI applications. Traditional databases excel at precise queries. Find all records where status equals active or where timestamp is after yesterday. But AI agents deal with human language and concepts. When someone asks about database exposure policies, a traditional database would need the exact phrase. A vector database understands the documents about public endpoints, internet-facing services, and external access controls are all relevant to that query. It's the difference between searching for exact keywords and searching for meaning. Vector databases achieve this semantic understanding through embeddings. An embedding is a numerical representation of meaning. Text gets converted into a list of numbers that captures its semantic essence. When you store a document in a vector database, it first passes through an embedding model like OpenAI's text embedding 3 small, I think, or open source alternatives like sentence transformers, for example. This model transforms your text into a vector, typically with hundreds or thousands of dimensions. For example, PostgreSQL database must not be exposed to the internet becomes a vector like 0.023 minus something something and so on and so forth, with 1,536 dimensions. The magic is that similar concepts get similar vectors. Let me demonstrate this. I'll take one sentence about database security and compare it against 5 other sentences to see how similar their vectors are. Look at those scores. The script converted all 6 sentences into 1,536 dimensional vectors, then calculated how similar each comparison text is to our base text. PostgreSQL database must not be exposed to the internet. Don't allow public access to databases gets 0.6, the highest similarity. Even though it uses completely different words, its vector is very close to our base vector in 1536 dimensional space. It's expressing the exact same security concept. Then keep MySQL instances private scores 0.471. Its vector is moderately similar, even though it mentions MySQL instead of PostgreSQL. The embedding model understands they're both about keeping databases private. But here's where it gets interesting. How to optimize database performance only scores 0.276. Yes, it's about databases, but its vector points in a different direction because it's about performance, not security. The embedding model understands this distinction. And how about recipe for chocolate cake? Well, it's 0.01. Its vector is almost perpendicular to our database security vector. The model knows this has nothing to do with database security. That's the magic of embeddings. They capture meaning in mathematical space, not just keywords. Once text is converted to embeddings, vector databases store those high-dimensional arrays in specialized data structures optimized for similarity search. Instead of traditional indexes designed for exact matches, they use structures like HNSW, or hierarchical navigable small world, graphs, or IVF, inverted file indexes. These allow the database to quickly find vectors that are close to your query vector in multi-dimensional space. It's like organizing points in space so that you can efficiently find all the neighbors at any given point, even when that space is 1,536 dimensions. When you search a vector database, your query also gets converted to an embedding using the same model. The database then finds the stored vectors most similar to your query vector using distance metrics like cosine similarity or Euclidean distance. Cosine similarity measures the angle between two vectors. Identical concepts have a similarity of 1, completely unrelated concepts approach 0, and opposite concepts approach -1. This is why database exposure policies can find documents about public endpoints with a similarity of 0.85, while the recipe for chocolate cake would score near 0. The database returns results ranked by similarity, giving you the most semantically relevant documents first. Let me show you exactly how this works. I will search our vector database for an answer to a critical security question. First, I need to convert this question into an embedding, the same 1,536 dimensional vector format we use when storing our documents. Let's see what our question looks like as a vector. That's our question as numbers, just numbers. Now I will search Qdrant for the vectors most similar to this one. Perfect. Look what just happened. I asked, can I expose my database to the internet? And the vector database found an architecture decision record explicitly stating no database should be directly accessible from internet with 59% similarity. Then a security policy requiring cluster IP only, never load balancer with 43% similarity, and an actual incident report about the database breach caused by exactly what I was asking about, with 36% similarity. Now, notice that none of those documents contain the exact phrase expose database to internet. The ADR talks about directly accessible, the policy mentions load balancer, and the incident describes a breach. But the vector database understands the semantic meaning of my question and found the relevant policies, decisions, and even historical incidents. If I had used traditional keyword search for expose database and internet, I would have found nothing, 0 results, none, 6. But with vector search, I got exactly the information I needed to prevent a security incident. The key benefits of vector databases for AI applications are transformative. Semantic search means your AI agents can find relevant information regardless of exact wording. Instead of maintaining complex keyword mapping or synonyms, the system naturally understands that shut down the database and terminate PostgreSQL instance means the same thing. Scalability comes from specialized indexing algorithms that can handle millions or billions of vectors while maintaining sub-second query times. And performance isn't just about speed, it's about finding the right information on the first try and eliminating the repeated scans and failed searches that plague keyword-based systems. This combination finally gives AI agents the ability to efficiently access organizational knowledge the same way humans do, by understanding meaning, not memorizing exact phrases. The real power comes from what organizations actually store in vector databases. Everything becomes semantically searchable. Kubernetes manifests, Terraform configuration, security policies, runbooks, architecture decisions, incident reports, API documentation, even Slack conversations about outages. But here's the thing. You don't just dump entire documents into a vector database. Remember, each piece of text needs to become a meaningful embedding. A 50-page runbook as a single vector would be useless. Instead, you need intelligent, chunking, breaking documents into semantic sections that maintain context while being specific enough to be useful. This chunking process is where things get interesting and complicated. How do you chunk a YAML file? Where do you split a troubleshooting guide? How do you maintain context across chunks? What metadata should you preserve? Those aren't trivial questions. I'm not going to lie to you. And bad chunking can make your vector database nearly useless. But don't worry about losing access to complete documents. When semantic search finds a relevant chunk, you can always retrieve the full document it came from. Think of it like a smart index. The vector DB helps you find the relevant paragraph, but you still have access to the entire document when you need broader context. This is exactly how RAG systems work in practice. They search semantically at the chunk level, but can expand to full documents when generating responses. Now, if you're interested in diving deep into document chunking strategies, embedding optimization, and building production-ready vector databases, let me know in the comments. It's a fascinating topic that deserves its own dedicated exploration. For now, what matters is understanding the transformation. Your organization's knowledge, previously trapped in various formats and systems, becomes a unified, semantically searchable knowledge base. A vague question like database keeps disconnecting can instantly surface relative information from runbooks, past incidents, or Slack threads and documentation, even when they're using completely different terminology. Now, RAG, or Retrieval-Augmented Generation, is the bridge between your vector database and AI's responses. Instead of relying solely on what the model learned during training, RAG dynamically pulls relevant information from your vector database and includes it in the AI's context before generating a response. It's like giving the AI a reference library card. Before answering any question, it first looks up the most relevant documents or policies and examples from your organization's knowledge base. This transforms a generic AI model into one that speaks with your organization's voice and knowledge. Now, you're already experiencing a form of RAG when you use coding agents like Claude Code or Cursor. When you ask about your codebase, they retrieve and read your files before responding. Current agents use brute force retrieval, scanning directories, reading entire files, searching for keywords. They might read 50 files to find one relevant function, or scan every policy file to understand a single rule. With vector databases powering RAG, the same query triggers semantic retrieval. Instead of scanning everything, the system finds exactly what's relevant based on meaning, not just text matches. Your question about database configuration instantly retrieves the relevant policy sections, the related ADR explaining the decision, and similar resolved issues, all of those ranked by semantic relevance. But wait, if brute force search is so inefficient, why don't we just put all our source code in a vector database? Huh? Good question? Well, you could, but code is different from documentation. Code changes with every commit, requiring constant re-indexing. Code needs its full context. Imports, class definitions, surrounding functions, vector databases chunk content into pieces, which can break those relationships. When debugging, you often need exact matches for function names or specific syntax patterns, not semantic similarity. That's why coding agents still use traditional code analysis for active development. But code comments, docstrings, example snippets in documentation, historical implementations? Well, those are perfect for vector databases. They change less frequently and benefit from semantic search. So, we need both traditional file access for active code development and vector databases for organizational knowledge. But let's focus on how RAG works with vector databases, since that's what transforms AI from a generic assistant into one that knows your organization. Let's walk through what happens when someone asks, how should I handle database backups? They don't need to know where the answer lives or what keywords to use, they just ask. The AI agent receives this question and immediately sends it for embedding. This could be Claude Code, Cursor, or any custom application, but they follow the same pattern. The query goes to the same embedding module that indexed your documents. This part is crucial. You must use the same model for both indexing and queries, otherwise vectors might not align. Then the embedding model works its magic. It converts the question into 1536-dimensional vector. This vector represents the semantic meaning of how should I handle the database backup as a point in high-dimensional space. Now, the agent takes this vector and searches your knowledge base. It's looking for document vectors that are close to your query vector in that multidimensional space. The vector database calculates causing similarity between your query and every stored chunk. Now, within milliseconds, similar documents come flooding back. Your backup policy scores, 0.88 similarity. Very relevant, right? The Cloud Native PG guide scores 0.72. Also useful. Even though your questions never mentioned Cloud Native PG or 30-day retention, the semantic search found those because they are conceptually related to database backups. And here's where the magic of RAG happens. The agent doesn't just pass your question to the LLM. Instead, it creates an augmented prompt that combines your original question with the retrieved documents. It's essentially saying to the LLM, based on these specific documents from our organization, answer this question about database backups. The LLM processes this augmented prompt and generates a response. But unlike a generic LLM response about database best practices, this answer is grounded in your organization's active policies. It knows to use Cloud Native PG because that's what your documents say. It specifies 2 a.m. UTC and 30-day retention because those are your real requirements. Finally, you receive an answer that's specific to your organization, like use Cloud Native PG with daily backups at 2 a.m. UTC, 30-day retention, and so on and so forth. The complex organization remains invisible. You asked a simple question and got a precise contextual answer. The entire process takes seconds. Actually, it takes longer if you need to retrieve actual documents, but at least the vector DB part takes milliseconds. And the impact is profound. The AI no longer hallucinates generic answers. It responds with your organization's specific knowledge. One of RAG's most powerful benefits is reducing hallucinations. When an AI model doesn't have specific information, it tends to make plausible sounding guesses. Ask a generic model about your Cloud Native PG backup policies, and it might confidently describe best practices that have nothing to do with your actual setup. With RAG, the model's response is grounded in retrieved documents. When asked about backup policies, it retrieves your actual runbook, your team's decisions, and your implemented configuration. The AI can still use its reasoning capabilities to synthesize and explain, but it's working with your facts, not with fiction. This grounding in real documents dramatically reduces those confident but wrong answers that make pure LLMs risky for production use.
It's all FAKE. The AI is seeing things that aren't there. It's having digital hallucinations.
So, if you're one of those people, now you know what to do. You're probably asking AI about information it never had access to. Of course it's making stuff up. Feed it your actual documentation, your policies, and your decisions through RAG, and watch those hallucinations disappear. The problem isn't AI. The problem is you. Another game-changing benefit, dynamic knowledge updates without retraining. Remember that impractical train a custom model approach? With RAG, you skip all that. Updated your backup policy? Just reindex that document. New architectural decision? Add it to the vector database. Resolve the critical production issue? Index the postmortem. Your AI's knowledge updates immediately. No model retraining, no waiting for the next release, no MLOps pipeline. This is how you keep AI current with your ever-changing infrastructure and policies. The model stays the same, but its accessible knowledge grows and updates continuously. Now, let's see this in action with something more dramatic. A developer tells your AI agent,
Computer, deploy PostgreSQL for payments in production now. Make it handle real money.
Without RAG and vector databases, the agent might create a basic stateful set with a generic PostgreSQL image, expose it with load balancer service because that seems reasonable, right? And it can use local storage because that's what the tutorials show. Congratulations, you just violated 3 company policies and created a security nightmare. With RAG powering the same request, here's what happens. The agent query becomes an embedding that searches your vector database, it retrieves your database deployment standards, with, let's say, 0.94 similarity, the ADA mandating cloud-native PG for all production databases with, let's say, 0.91 similarity, your security policy prohibiting public database endpoints, the network policy templates for database access, and the post-mortem from when someone accidentally exposed the database. And now the agent knows exactly what to do. It creates a cloud-native PG cluster with your standard configuration, applies the required network policy, sets up encryption with your KMS keys, configures backups for your S3 bucket with 30-day retention, adds the mandatory security labels, and even includes monitoring annotations for Prometheus. Every single detail follows your standards. The difference isn't just correctness, it's the difference between a security incident and a compliant development. Do you remember that rant at the beginning about how AI doesn't work, hallucinates, doesn't understand your code or infrastructure? Now you know the truth. The problem was never AI. The problem was you. You were asking questions about information the AI never had. You were expecting magic instead of implementing solutions. You were treating AI like it should somehow know your organizational knowledge through osmosis. The solution exists. Vector databases for semantic search, embeddings to understand meaning, RAG to ground responses in your actual documentation. Not someday, not in the future, right now. Every single day you don't implement this is another day of your developers getting generic code advice instead of team-specific guidance. Your ops team receiving hallucinated procedures instead of actual runbooks. Your AI agent scanning through files inefficiently instead of finding exactly what they need. Your engineers dismissing AI as not ready, when actually it's actually your implementation that's not ready. The tools are there. Pinecone, VV8, Qdrant for vector storage, OpenAI, or open source models for embeddings, well-documented RAG patterns. Hell, you could have a proof of concept running by tomorrow. So, what's your excuse now? Too complex? I just explained it in one video. Too expensive? The cost of continued manual work is higher. Too much effort? Well, no. It's less effort than what you are currently basing on tasks AI could handle. So, stop complaining, stop making excuses, stop pretending AI is the problem when you're the one refusing to implement the solution. Because the only thing standing between you and the AI that actually understands your organization is you. Thank you for watching. See you in the next one. Cheers.